I have just a few slides on our radio and access point capabilities. So just to highlight what we do provide is we do provide indoor and outdoor access points. Our indoor ones are very similar to Wi-Fi. They provide dual radio with internal antennas, 2x2 MIMO today, higher orders of MIMO coming in the future, especially with 5G. Up to 36 dBm, which is very comparable to many indoor wireless solutions today. And it requires PoE plus for powering or an optional AC power. So very similar to what you might be used to hanging access points off of your ceilings or walls and inside in facilities. On the outdoor side, it's kind of interesting. We have, again, dual radio, 2x2 MIMO, N-type connectors. It's IP66 rated for kind of weather and harsh conditions. It is AC powered since it does draw quite a bit more power, up to 60 watts. And that really gets into the higher power output that it's allowed to operate at as a Class B CBRS device, up to the 47 dBm or 50 watt EIRP output on these units. And these will be mounted on pole outdoors with directional antennas to cover specific targeted areas. Or you can do an omnidirectional antenna as well to cover just large generic outdoor campus environments.
Is the indoor access point's internal antenna, is that an omni or is it directional?
They are omni and they have a few degrees of down tilt.
Excellent.
Any plans for these to be rated for industrial use, class 1 div 1, class 1 div 2 environments?
That I do not know. I know our current model for outdoor right now is IP66. I don't believe we have any other certifications than that. Mehmet or Rajiv, do you have any roadmap on some of those other certifications?
Yeah. We are getting that request from some verticals and looking at it closely. It's a matter of just pulling the trigger on that. It's just very doable, but it takes some effort and time. And we'll do it. I don't know exactly when though.
Real quick, refresh my memory here. The client max power is 23 dBm. Is that right by the standard?
Correct.
Okay. And so we're seeing a huge gap there between, capabilities of the AP and capabilities of the client, right? By standard. Where do you see the need for the much higher power? If our clients, I understand a little bit of, maybe 3 or even 6 dBm greater, but that's a huge gap there. What am I missing?
Yeah, JD, great point. Sorry, and I'll just jump in. This really comes from the design of the LTE and 5G, right? The uplink is designed with a much lower noise figure, and it's single carrier FDM versus the OFDMA. Because if you think about it today, right, you can use your phone to reach the base station maybe 2 miles, 3 miles away. So the uplink link budget is designed with that power limitation in mind.
Yeah, okay. As soon as you said that made sense.
Yeah. Great question.
Excellent. So to keep moving along then, once you have your client devices kind of identified and provisioned, then you need to look at planning your infrastructure deployment. So like I mentioned previously, there's a Celona network planner to give you a rough order magnitude of the number of APs you might need for a given scenario. This is a free tool, web-based on planner.celona.io. And you can put in the facility type. It has back-end regression modeling to understand how those environments typically perform from an RF link perspective. And we'll give you spectrum availability as well for that location from a CBRS and spectrum access system database query. And you can put in very specific app and device requirements as well for capacity reasons. The Celona Network Planner is also driven by an API. So that's one thing we're going to stress throughout the rest of this conversation is that we're an API first driven solution. So if you have multiple sites that you need to plan for, you can do that very efficiently by leveraging the API on the network planner to very quickly plan and estimate the number of access points required across a large number of sites. And you can also do continuous monitoring of your spectrum availability through this to understand when additional deployments may be coming on around you from a neighbor perspective, who's deploying in the areas around your radios. So you have some visibility into that. Another key feature of our radios then are the self-organizing network capabilities. And so this really has three main components. First is SAS integration for CBRS spectrum allocation. So the Celona Edge as a packet core function has spectrum management capabilities built in. So for a collection of access points, this could be across one or multiple sites, the Celona Edge will query the spectrum availability for all of those radios, and then also coordinate the most optimal channel and frequency assignments and get spectrum grants automatically from the SAS database provider for those radios. So everything is automated on the back end as part of our solution to integrate with the SAS database providers. The second key feature is that dynamic channel and power allocation. Just like you may be familiar with radio resource management, a self-organizing network can understand the coverage and capacity requirements within your network and optimize those across your radios so that the channel allocations are most optimally assigned to avoid interference where possible, given the set of channels and available based on the SAS spectrum inquiry and grants. And then this is a closed feedback loop based on the channel state of the radios as well. So the radios and the scheduler within the radios are constantly providing key performance metrics back to the Celona Edge so that these algorithms can be refined and the network operation can be optimized as well. So if radios are experiencing poor performance, they can send that information back to the Celona Edge, and that will be used to close that feedback loop and improve the network further. A key aspect of LTE and 5G on our access points is wireless link reliability. A couple of key reasons why link reliability in LTE is very robust are link adaptation, traffic scheduling, and error handling. From a link adaptation perspective, client devices send feedback on their channel quality all the time back to the base stations or access points. This is through CQI or channel quality indicators. And so the infrastructure has a view of how every client device sees the RF network and the RF link state to understand how it's performing. And the infrastructure can actually control the client devices and tell them which modulation and coding scheme to use based on their RF quality. So one of those key aspects then is that infrastructure control of what data rate adaptation that the client devices are using to send traffic in the uplink direction as well. Second is traffic scheduling. So just like it communicates the modulation coding to use to each of the clients, it also tells the clients when they can transmit in the uplink direction as well. So based on those CQI reports, it can also select very specific frequency subcarriers that may be performing better than others and assign those subsets of frequency tones to the client devices and the applications that require the higher levels of QoS and reliability. So if we have multiple clients needing access onto a LTE access point onto the channel, we can assign the frequency tones that are performing the best to those clients requiring the most robust QoS and SLA kind of characteristics. And then third is robust error handling. So there's forward error correction built in with hybrid automatic repeat request and soft combining so that retransmissions don't need to send the entire frame or packet back if it was corrupted. Only those subsets of data need to be retransmitted if necessary. And they also go a step further with the soft combining to try to avoid retransmissions altogether, where the decoder can potentially have enough parity information in the encoded data to recover the frame even in the midst of some noise or errors. So very robust error handling built into the physical layer. And then the last aspect of the Celona access points I'd like to talk about is that infrastructure controlled mobility. So handoff between APs is always a very finicky topic, especially for certain applications that are very sensitive to network delays or network drops. In LTE and in the Celona solution, there's two forms of handover between LTE access points. One is called backward handover, and that's where the network or infrastructure controls that handover between eNode Bs. So device measurements are always reported back to the current access point that the clients are connected to. And when that client device is transitioning between APs, the current AP informs the new AP in advance to prepare for that handover. So all the client state information is transferred over to the new AP. And then the current AP instructs the client device when to perform that handover. And there's very well-defined thresholds on how long client device has in order to execute that handover. So that's kind of the more typical use case for handover, where it's infrastructure controlled. There is a fallback mechanism to a radio link handover, where essentially a device can say, in an emergency situation, something has changed, it needs to immediately transition to a new access point, and the client device can trigger that itself. That's more typical if there's an actual link failure or quality has degraded over a very short period of time. And the client device can immediately transition to that new target AP, and the target AP will request the context from the current AP. So there's two methods of handover and very robust, defined communication between the client and the access point of the RF channel state that happens at all times.